Hello, so this is my summary of lecture 24. So this is the Fourier series part. I will begin by summarizing what I read from book and then what I understand from the lecture. Okay, so let's start with our example of a vector. So what we have been learning so far about vector is that we know that this one is a vector and this one has 3 components. Okay, and now what about vector? So we say that these lives in R3, right? It has those 3 components, but what if some vector that lives in Rn? So something that has infinite component there. Okay, so this is what will bring us to the Fourier series. And then let me continue. How about the length of this infinite vector? So I'm interested in, let's say I have v, that is v1, v2 till vn, and then I have w, w1, w2, and then of course, you know, I need the length, so easiest way is to dot them, so vtw, so I got like v1 w1 until vn wn, right? And the question is this finite or will this go blow up? Okay, so it depends on the vector v and w. So in case of the infinite, let's say v equals w equals, so all those components are 0, right? Of course, it makes sense that vtw, which are the length squared, I just want to remember you guys, this is not the correct way, right? But you get what I mean. Length squared, there you go, squared. Okay, so this will go to infinity, of course, but there is some finite case. So this is the case where v and u is some kind of like beautiful series that is defined by the geometric series. So in this case, for example, if I dot, so b dot u will be 1 times 1 equals 4, because half times half, and then a quarter times a quarter, then 1/16. Then this is actually, this kind of series can be defined by this formula, 1 over 1 subtracted by quarter, this will be 4 over 3. So what I want to say here, that there are 2 cases, right? So those infinite vector can have infinite length, or it can have finite length, like in this case. Okay, so we have gone to this point, and actually this brings me to the definition of the Hilbert space that is briefly mentioned in the book. So the Hilbert space says that the vector v that has that infinite numbers of component and a function fx. Now let me talk about this more, but Hilbert space is not just about a vector, that's a fact that I want to show you, but it's also a function is defined there. So imagine that instead of having a vector, we're having a function there. So we can have the function that can also behave like a vector there. Okay, and let me continue the definition of the Hilbert space. So lives in our infinite dimensional Hilbert space, I will just abbreviate it by HAs, if the length square is finite. Okay, so let me underline those two things. So again, so this vector and functions are like infinitely long, right? But the length of them is finite. Then we can say that that vector or that function lives in our Hilbert space. So that's just a really quick introduction, because that's also introduced in the book. I just want to mention it here. So that's the Hilbert space. And then now let's bring back our focus here. So I say that this is also in the space we can also have the function. So not only a vector like what we have been learning so far. What I want to say is that for vector, you might have those components, and then it will bring you to a point, and then you have a vector which points to that point, right? But in a function, imagine function is just infinitely long. It's just continuously long function. So it goes so infinitely long, right? And then we can also consider this function and treat them as if they're vectors. So that also means we can do the length computation. So for vector, we have our vector length is the v times v, okay, which is the v1 squared plus v2 squared and until vn squared. And now we can also do the same thing. So we can the length squared of that function. See? But the notation changed, and pay attention to the notation here. So f and then the dot is changed to a comma, and then this, how do I define that addition in terms of function? So imagine I want to add all these little pieces. So actually that's what we learn in the calculus. We integral, and then we have the square of it, right? Because it's also squared, you know, remember this is just like the dot product, and this is the like dotting our functions. And then we give them the limit from 0 to 2 pi. And the reason I give 2 pi here, because in our next example we will just mainly talking about the sine x and cos x. And for both of them, the fx equal to fx plus 2 pi. So that's why it's just repeating. So this is our limit. Okay. So let's try some example. Let's give it example here. Let's say my fx is sine x. Okay. And I'm interested in the length of f, length squared. So what do I do? Let's just get used to the notation, and then set a limit 0 to 2 pi, and then this will be sine x squared, right? And then this is basically you can use the trigonometry identity and so on, but this will bring us to pi. So the length of the sine x is length square is the pi, and then the length of f is the square of pi. So that's a quick example I can give you. And by the way, regarding the notation, so if you have two functions like f and g, then you will have like f comma g for the inner product, and then you will have the integral of fx gx to the dx. Okay. Now, last point that I want to discuss is that in our next example that I want to discuss is that the cos x and the sine x are orthogonal in the function space. So let me repeat that. So the cos x and the sine x are perpendicular or orthogonal in the function space. So what are the implications of this is that, let's say my f is cos x and then my g is sine x, okay? And if I do the inner product of them, then this will be 0. And this is not just for the x, the lists are continuous. For example, the same goes for cos 2x, sine x, or sine x 3x with cos x, and anything. And this will be useful. These are our building blocks for our last 2 points here, the orthonormal basis and Fourier series. I'll see you there.